So if the professor said that if you make sure your thesis is like airtight, then the rest of your paper will fall in place. So I guess that's what I'm looking for to make my thesis as strong as possible.
So the question is about flight overbooking, right?
Mm-hmm.
Okay, sure. So first, this is a Poisson distribution, right? Because uh, it's kind of like a binomial. So basically, the Poisson distribution is an approximate approach to estimate the binomial distribution because they have the same format. There's two possibilities in total, showing up or not showing up, and both of them, like either of these two possibilities, have a particular probability, right? So the probability of showing up is 0.01. The probability of the probability of showing up is 0.99, and the probability of not showing up is 0.01. So basically I have two possibilities, and each of them I give them a number between 0 and 1 to make them add up to 1. So they have their own possibility. It's basically the format is similar to tossing a coin, right? But the difference is when I toss a coin, the probability of a head and a tail is both 1/2. That is relatively high. But in this question, the probability of not showing up is only 0.01. That is very, very low. So if this happens, right, that is a hint for us to use the Poisson distribution to estimate the binomial distribution. So basically for question number 2, you can think about it as tossing a coin, but in that sense, the calculation is very complicated because the sample size, the observation is very large. It's not like tossing 10 coins. Here you're talking about 400 passengers. So if you use the binomial formula, you cannot do it without like a computer. But the good thing is because the probability here is 0.01 and 0.99, one of the probability is very, very low. That means we can use the Poisson distribution to estimate. And the formula for Poisson distribution is relatively easy. So basically that's some introduction to the Poisson distribution. And
Mm-hmm.
I'm not sure if you can see my solution here on this page. Sure.
Hold on.
I can
Okay, so that's.
stop.
Oh no, I was
share
able to
again.
see it, but now it went away.
Sure. Nice. That works. Question 2, right?
So this is A.
Right. So if you have a chance to look at the formula for the Poisson distribution, there is a very important parameter called lambda.
Mm-hmm.
Right. So lambda basically is the multiplier of n and p, the total observation times the possibility. In order to use the Poisson distribution, you have to have a very big n and a very small p. And basically, this question matches the Poisson distribution. So first you calculate lambda, which is n times p, is 4. And then you kind of just plug in your lambda into the Poisson distribution formula. Basically, the probability of 400 people showing up is just Poisson 0. And then 399, because let's just do one example, maybe 398 people showing up, the probability of 398 people showing up. This statement is exactly the same as the probability of 2 people not showing up, right? They're exactly the same. Just inversely state that. So basically the probability of 398 people showing up is just Poisson 2. If you plug in, if you look at your Poisson distribution formula, that is lambda squared
Mhm.
divided by 2 factorial. 2 factorial is just 2 times 1. So the numerator is just 2. The denominator is just 2. 2 times 1 equals 2. And then times e to the power of negative lambda. And you plug
Okay.
in your lambda equals 4. And basically you get your probability.
Okay. And like this, so like the 4 probabilities you have there for like A, are you
Yep.
using, so I see you're using like 0, 1, 2, 3. So is that what we're supposed to use? We're not supposed to use 3, like 400, 399, 398.
Now here is the thing, like because so remember when you calculate your lambda, you use n times p. And what is
Mhm.
your p? P is 0.01,
Over
right?
shareholder interest.
What does
Correct.
that mean? 0.01. It is a probability of passengers not showing up. That probability is 0.01. So when you plug in lambda to your formula, you are
Mhm.
actually calculating the probability of how many people not showing up. So you cannot use P400 because if you use P400, that is the probability of 400 people not showing up. That's not what you want to get. You want to get the probability
Oh.
of 0 people not showing up.
So yeah.
Okay. I see what you mean then.
Yeah.
Okay, that explains. So you just did n times p, and then for the b makes sense, and then I get tripped up at the c. Is c just you do like all the probabilities, and then like probabilities of 400 through
So
like
basically, I mean,
96.
in this question, the wording is a little bit confusing, but so
Mm-hmm.
basically,
Yeah.
you are you are the first in line on the waiting list. That means you are the passenger number 401.
Okay.
That's the meaning of this question. So basically, in order to fly, like considering you are the passenger 401, you need to have more than 396 people not showing up.
Okay. So you do the probability of. So I have to find the probability of the 4th person not showing up,
Yes.
and
So,
then
yeah, so
subtracting it from like basically like what I get from B.
yes, exactly right.
Oh, okay. Okay. Oop, wait, are you still there?
Yeah, sure.
Sorry, I just I'm on my phone again and it shut
Yeah,
off.
never mind.
Okay, and then another question from the homework. This one's really quick too, also. So he did go over like number 3, like the radioactivity, and like explained us the exponential. So that's really just the answer is just e to the -2 lambda t. Is that just the answer?
Yeah.
Okay, I guess. And then for the explanation for the first one, I also didn't get like what am I supposed like what like from am I also supposed to add up all the numbers in number 1?
Mm,
I did Poisson for number 1, and I did Poisson for 0 through 5. Am I supposed to add up all those probabilities, or is that only when you're doing binomial?
You're talking about question number 3?
Question number 1, sorry.
Oh, well, question number 1. You're doing Poisson. You're doing Poisson. Binomial is like basically so for all the question, if you can do it with Poisson distribution, you can absolutely do it with binomial, because
Okay.
binomial is more accurate and Poisson is just an estimation. However, you see the total number of hitting I calculated here is 535. That means if you go to a traditional binomial distribution, the example of tossing coin, you are tossing 535 times, and the calculation could be very difficult, and it's not possible to be done by hand. And so basically, when you see a very large number of observations plus a very low number of probability, then you can use Poisson to estimate. And that is what exactly the professor supposed you guys to do.
Okay.
So again, you calculate the lambda and and zero hits, the probability of zero hits and one hits and two hits, etc. 4 hits, 5 hits, and then you calculate the probability, and then you use your probability times the number of observations, which is 535. You get your frequency, and you
Why do we
and
have
this
to do the?
frequency,
Oh, sorry.
right? So basically, this frequency is a theoretical frequency if the if the bombs are following a random distribution, and then you compare your like theoretical frequency to the actual frequency that's being observed, and to see if there exists a very huge difference. If there's no huge difference, that means basically the bombs are landing at random.
Okay. So we just multiply each number by, and then is our answer the theoretical frequency or the actual probability?
So in this question, I think you have to calculate the theoretical frequency because here you have your actual observation, right? There's 229 sectors with no bomb at all. There's 211 sectors with one bomb, etc., etc. So that is your actual observation. And then, so basically you assume those bombs are landing at random, and that gives you the power to use the Poisson distribution to calculate the theoretical frequency if those bombs are landing at random. And then you find out, right? Oh, if the bombs are landing at random, theoretically, I should observe 211 sites with no bombs at all. And then you compare 211 to your actual observation, which is 229, and you say there's no huge difference, right? And then the theoretical frequency of one bomb is 196 section. Then you compare your 196 theoretical sections to 211, which is your observation. And there's some difference, but you know, statistics, it's all about probability. So those differences are just caused by chance, more likely caused by chance, not because my bombs are like advanced technology that can choose like the target to hit. So basically, it's very likely the bombs are just landing at random.
Okay, but do we have to add up all the theoretical frequencies in the end?
Not necessarily. And actually,
Well, it looks like you
not
didn't.
necessarily. I think when you add up those numbers, you will get a number very close to 535. Because like generally, it's very less likely that in one section, in one sectors, you can find 6, 7, 8, or even more bombs, right? It's very less likely, even in the simulation of Poisson distribution, right? So in our actual observation, there are only one case where a section is hit by 5 or more bombs, right? But we build the model of Poisson distribution, we simulate the number. It's still very less likely that you get 6, 7, or 8 bombs. And actually, if we add up all those theoretical frequencies, you find a number very close to 535. Because like although I didn't write about P6, P7, P8, etc., those probability are very, very low, and we can actually ignore it. Like
Did we say should I say extrapolating dependent instead of generalizing dependent?
Sorry, what? Hello?
hello,
Yes,
you hear me?
I'm still listening.
Sure, sure. Well, like one example that I think is intuitively easy to understand is you buy lotteries. That is like perfectly aligned with Poisson distribution because you can buy, for example, 1,000 lotteries. That means your N is very huge, or number of observations is very huge. And the probability of winning a prize is actually pretty low. So basically buying lottery is a perfect example of Poisson distribution. And think about it, what is the probability of winning 6 times when you buy 1,000 lotteries? It's actually very low. And what about 7 times, 8 times? What about you win 20 times when you purchase 1,000 lotteries? The probability is essentially zero. So you don't have to consider those things. You only consider the probability of not winning, winning 1 time, winning 2 times, all the way winning 5 times, because that is basically aligned with our observations.
Okay, I see what you're saying, but in general, like when you find your probabilities with Poisson, will you add them together, or is that just binomial? That's like what I'm trying to figure out. Do you like understand what I'm asking?
Um, I would say here the P0 means the under Poisson distribution, the probability of observing zero bomb is 0.395. What you can do is you can use a binomial distribution to calculate it, and you will find a very close number. So the P0, for example, I say the Poisson under Poisson distribution, the probability of observing zero bomb is around 0.395. And you can calculate under binomial distribution, the probability of observing zero bomb is actually very close to 0.395. And that's easy to calculate, right? Because it means like in each observation, there's no bomb at all. What is the probability of not finding a bomb in my first observation? Is just 1 minus p. It should be 575 divided by 576. And then you use this number to the power of 535, to the number of our observation. Then you get the probability, which is under binomial distribution, of not finding any bomb in one section. Basically, that is a number very close to 1, but a little bit smaller than 1, to the power of 535. And basically, we'll get a very, very similar number to 0.395. You can do that experiment. I don't think you can do it by hand because it's a fraction to the power of 535. And and again, that is one of the biggest advantage of Poisson distribution, because mathematically you can prove when n approaches infinity and when p approaches zero. That's what I said, when your observation is very big and when the probability is very huge, and the Poisson distribution approaches the binomial distribution. So that's a very good way to estimate.
Okay. I think that's all the questions I have. Thank you.
Sure.
I'm just gonna stick around so I can hear what Yvonne has to say
Definitely.
too.
Definitely.
Okay. But I'm done. Yes.
I would just want to ask some basic stuff, like actually I want to ask like under what situation are we gonna use the hypogeometric distribution? Like I was pretty confused. Like I know how to use the binomial and also Poisson distribution, but I don't know like under what situation are we gonna use the hypogeometric, the uniform, and exponential one.
Sure. So first, after the session, I'll probably provide you guys a link because I find a similar problem when I'm grading your third homework.
Yeah.
I think like many of you guys use the binomial distribution when the question is asking about the hypergeometric distribution. Um,
Yeah.
but so to answer your question right now, I would say hypergeometric distribution is first you do a selection, right?
Yeah.
You do a selection, and basically you divided the whole group into two parts. Then you have to make a selection in either of those parts. So an example, I don't think is a very good example because it involves a lot of numbers, but I cannot think about a better example. Right? If there's 10 balls, 5 of them
Yeah.
are red, 5 of them are blue.
Yeah.
And I said, what is the probability? So first, I randomly select 2 balls. What is the probability of selecting one red ball and one blue ball? Right, so this is a very typical example of hypergeometric distribution. The way to
So
solve it,
hypergeometric is like when the situation happens like there's not two options but like a lot of it.
yes, there's a lot of options. And basically those options in the formula lies
Yeah.
on the denominator. So when I ask you what the probability of choosing 2 balls and find exactly one blue and one red, right? You're gonna use a
Yeah.
formula, right? That formula, the denominator of that formula is actually 10 choose 2. It's all the possible options you have, right? There's 10 balls and you choose 2 balls at random. How
Yeah.
many ways you can do it? It's just 10 choose 2, right?
Yeah. Yeah.
So that's in the
Oh,
denominator.
so hypogeometric is about like 10 like choosing like C, right?
What do you mean
Like
choosing?
it's
So like we call
just
that
like
combination.
yeah. I'm
Yeah,
sorry
call
about
that
that.
a combination.
Yeah. Like is that hypogeometric only about combinations?
It's all about combination.
Okay, yeah, I get that. And also I'm pretty confused about exponential and uniform. And so also sorry to ask, can you explain it in Chinese?
I'm
You're not
I
Chinese?
can try that. Yeah, I am Chinese, but like I don't really know those terms in Chinese. Some because I'm learning that
Oh,
in English, so I'm not too sure if like I can
okay,
convince you
yeah.
those
Can you
terms.
try to use that because I'm not sure like what are those actually means and like it's a little bit confused for me to like understand it in English.
Okay, so first I may stop sharing. Oh, because I'm kind of recording all the. Hmm, wait a second.